Thank you, Banayada. Hello, everyone. Welcome. So Mihalis and Konstantinos introduced us to large language models and some very, very complex models that unfortunately will not be able to do in an hour. So what I want to teach you is how to start building neural networks in PyTorch and how to use them on GPUs, which enables us to do all these things. I want this to be an interactive topic. So if you have any questions or if you don't understand something I say, please stop me and ask away. As I said, it's better if you want to follow along the Jupyter Notebook, you can run it in Google Colab. I'm going to be running through my laptop because Colab is a bit slow. Okay, so let's start. I'm sure you've seen this before. Everybody talks about AI and they mean everything from just a simple rule, though if I get home, just turn off my mobile data and connect to the Wi-Fi, down to large language models that can write an essay for you. There's a classification when we talk about that. Artificial intelligence is actually a very large family of anything that enables computers to mimic human intelligence. And that can be from, as we said, simple if-else rules down to very large models. Then if we go down to machine learning, that's a subset of AI. There we utilize statistical methods that enable machines to learn from examples and perform a given task. And this is not something new. This is something that has been formulated since the 50s, but it's only been able to do due to computational cost in the last couple of decades. Going even further, then we get down to deep learning, which is an even smaller subset of machine learning that enables software to learn from examples and perform tasks from very simple to very complicated, like speech and image recognition. And to do that, we utilize multi-layered neural networks, and we usually train them on large data sets because neural networks usually have a lot of thousands to millions up to billions of parameters. In machine learning, there's a lot of ways to train a model. Simplest ones are supervised and unsupervised. In supervised, we have labeled examples. In unsupervised, we don't have labels, so we actually don't know the correct answer, and we let our algorithm learn it, like clustering or, so advertisement companies try to cluster clients. There's also a lot of combinations of all these, like semi-supervised, when we have a huge number of examples, which is very, very expensive to label. So we label some, we let our model label the others, and then we train it again and hope it gets better. We have reinforcement learning, where the model actually learns by itself, and we come up with like a penalization factor that enables it to go to our desired answer. As we said, in deep learning, we use neural networks, and this is the simplest form of neural network. When we say deep, we usually mean that we have at least one hidden layer. In this example, we have two. So we always have an input layer and an output layer, and something in the middle, which we call the hidden layers. So again, neural networks is not a new concept. It's been mathematically formulated in the 50s or 60s, but we didn't really have the computational power to train them or use them in any efficient way until 15, 20 years ago. And not until like 10 years ago when we started using GPUs and more dedicated accelerated units like TPUs, tensor processing units, where we're able to do all those great models and use them basically everywhere. Now, to develop neural networks, there's a few frameworks available at the moment. We have TensorFlow, JAX, and here we're going to use PyTorch. PyTorch has been developed by Meta AI, the company that owns Facebook. They actually use it for the AI stuff they do on the services. I think it's one of the two most popular in the last few years. The other one is TensorFlow. No particular reason why I use PyTorch, just I like it a bit better. You can use that. So what actually is PyTorch? It's mainly written in Python, and it's a replacement for NumPy that can use GPUs to accelerate all the operations. Another great feature is that it's an automatic differentiation library that it's very important when you're trying to train neural networks. The main data structure in PyTorch that we're going to utilize here are tensors, and they're similar to NumPy's ND arrays. And using these, you're able to encode the inputs and outputs of a model as well as the model's parameters. As we said, the very significant difference between tensors in PyTorch and NumPy arrays is the ability of tensors to run GPUs or TPUs to accelerate computing. So we assume that you can install it. There's guides everywhere, and if you're using Colab, it's already there. So we can import PyTorch by using the import torch command, and also we're going to import NumPy so we can compare the two. To check if Torch actually can use the GPUs, we run this command, see if Torch CUDA, if it's available. If it's true, then it means that the Torch installation can see your GPU. Then we can number the number of devices we have. In this case, it's only one GPU. And then if you want to see which GPU you're using, you can use the get device name command. Now a bit more about tensors. As we said, they're very similar to NumPy arrays, and there's a few different ways to initialize a tensor. First, you can just initialize it from a list. In this case, I have a 2x2 list, 1, 2, 3, 4. And then we can pass that data into a torch.tensor method, and that utilize that. We can see that it creates a tensor with the same data in it. We can also pass a NumPy array in it. So we use the same data, that 2x2 list, to create an NumPy array, and then we pass that into the tensor. And we can see that it creates the same one. We can also pass another tensor to it to create a new one. We can retain the same properties. We can override these properties. Depends on our application. If you want to create a tensor that it's the same shape as the initial one, but full of ones, you can use the ones like command. If you want to create a new one filled with random data, which are randomly distributed, you can use the rand-like command. You can also define the type of the data you want to have in it. For neural networks, it's usually floats, so don't play around with that too much. And we can see that it's a new 2x2 tensor filled with ones and a new 2x2 tensor filled with random numbers. You can also define its shape. It takes a tuple of dimensions as an input. So we define a shape is 2x3 and initialize a random tensor and a tensor full of zeros with the same shape. Again, 2x3 random zeros. There's also a whole bunch of operations you can do with tensors. If you're using something that is mathematically heavy, doesn't necessarily has to be neural networks. You can directly replace NumPy arrays with that, and it's going to be much faster if your bottleneck is actually the computation. There's over 100 tensor operations. I'm not going to list all of them. You can follow this link into the documentation of PyTorch so you can have a deeper look in there. But the important thing to note here is that if you want to take advantage of the GPU acceleration, you should move them to the GPU if it's available. By default, when you create a tensor, it's always assigned to the CPU. So if you don't manually do that, then you're not going to get the GPU acceleration. Here we can set a device. So if CUDA is available, we're going to set it to CUDA, else we're going to set it to CPU. So can I see here that in the beginning, the device that the tensor was assigned to it was CPU. And then when we moved it by the 2 and the parentheses comma to the GPU, now it's on the GPU. If you want to index a tensor, again, it's just like NumPy arrays. So here, if we create a 4x4 tensor filled with ones and integers, and what we do here is we take all the members of the second column. Remember, Python indexes from 0, not 1. So 1 is actually 2 here. And set that all to 2. We can do that. There's also methods to concatenate tensors using the torch.cat function. And we can define the axis with the dim command. Here we're gonna concatenate the tensor we created above along the x-axis using dim equal 1 and along the y-axis using the axis dim equals 0. So see the 4x4 is now a 12x4 and 4x8. So, and what's so great about PyTorch and neural networks is that autograd function that's built into the PyTorch tensors. It's an automatic differentiation engine, and that what basically drives the whole neural network training procedures behind the scenes. You don't need to, unless you're doing something very custom, then you usually don't have to fiddle with these things. It can manage everything on its own just fine. And so why differentiation is so important in neural networks? When you're training in your network, that process happens in 2 stages. First stage is the forward propagation, where you basically go from the input layer to the output layer, and you do all these multiplications, biases, and activation functions, and then you end up with whatever is the output. But then there's a second stage in training, which is called the backward propagation. There, you go into the opposite direction, and the neural network adjusts parameters with proportionate to the error in its guesses. So it calculates the errors, and then it, using gradients, it's what we call gradient descent, it adjusts the errors, the weights and the biases in the network. It does this by traversing backwards from the output, collecting the derivatives of the error and with respect to the parameters of the functions, and it optimizes the parameters using gradient descent. So in PyTorch, all of this is done for you, and you don't need to worry about it. And in this example, we're gonna have a look at how that autograd functions collects gradients. And to start with, let's define 2 tensors. It's just a 1x2 tensor. And what's important here is that requires grad argument in the input. When you pass that, it means that it will enable autograd to track all the operations in there. So you don't have to worry about that on your own. And now let's create another tensor from these 2, say q equals 5 times a cubed minus b squared. And then we can print q2. So if you do the maths, it actually comes out to that. And just to make sure that PyTorch calculates the correct gradients, let's do that manual as well. So if we assume those two tensors are parameters and Q is the error, while training it, it actually takes the partial derivative with respect to A and B, which 5 times A cubed is 15 times A squared, and minus B squared is minus 2B. And this is all calculating the backwards method when you actually run the training. And then to do so, you have to pass another vector, just a unit vector 1, 1 in the backward method. Like this. And then all the gradients are stored in the .grad method. And if you actually do the maths, we can see that it's true. It matches. So in the next step, let's use all these to make a neural network to run through a classification problem. All the built-in blocks of neural networks in PyTorch are contained in the torch.nn package. And the NN package depends on AutoCAD to define models and differentiate them. All the modules you're gonna need, so all the actual layers are contained in the NN module. And then you need a forward and a method to actually come up to the output. So a typical training procedure for a neural network in PyTorch involves actually defining the neural network that has some learning parameters or weights, then to iterate over a data set of inputs, process that input through a network, calculate the loss, which always depends on what kind of model you're doing. And it's the difference between the model's output and the ground truth. Backpropagate the gradients through the network parameters, and then through the backpropagation, the weights of the network are updated, usually using this simple rule. It's weight minus the learning rate times the gradient. And in order to start building a neural network, we're gonna need some more inputs. As always, torch, the NN method, functional method is very useful. And we're also gonna need some data. Gonna need a dataset object, which is a method to load the data into the neural network. Gonna import datasets from Torch Vision, which is a method to abstract on getting some pre-existing datasets in Torch. To tensor transformation to actually translate images into tensors so the neural network can work with them, and matplotlib just to visualize them. In this example, we're going to use the fashion MNIST dataset. It's small enough to work in minutes and complex enough so we can learn something. It's comprised of 60,000 examples and has a test set of 10,000 examples, so it's total 70,000. It was published by Zalando. It's an e-commerce platform that sells clothes amongst other things. And each example is a 28 by 28 pixel grayscale image, and it comes with an associated image, a label from 10 classes. Here we can see the classes: t-shirt, trouser, pullover, dress, etc. If you want to learn some more, you can actually see their paper on this dataset in this link. So as we said, this dataset is available through the datasets module in Torch Vision. And in order to download this, we can run these commands. We need to define the root, which is where you want to store that data set. Train is a Boolean parameter. If it's true, you download the training set. If it's false, you download the test set. Download equals true if you don't already have it. And then we can define any transformations or target transformations we want to do it with our images. In this case, we just want to turn them into tensors. So we set the working directory as whatever the working directory is in Collab at the moment, and then you run the datasets.fashion mnist method to download it with the aforementioned parameters. I already have it downloaded, so it might take a couple of minutes for you guys. Is everybody okay up to now? Any questions? Next, we just have a simple method to visualize a few examples just to see what we're working with. First, we define a dictionary with the labels because they're just numbers in the dataset, so we don't actually know what each one corresponds to. And then we just plot the first 5 using matplotlib. It's a simple enough function. It takes random samples, so if you run it again, you'll get different sample. You can see you have a code, boot, t-shirt, sandal, no boot. In this case, because this dataset is already coming from PyTorch, all the abstraction is already done for you. But in case you want to load something else, like a custom one that you have a template custom image dataset function here that a class you can use here, and we can just run through it really quickly. We're not going to use that. It's just for you as a reference that it's there. When you're using custom dataset class, there's 3 functions that you need to define in it. One of them is the init one. It runs on the first time when you instantiate the dataset object. In there, you need to define where the labels are, where the images are stored, any transformations or any targets and transformations you want to do on the dataset. You need to brush off a bit on your object-oriented Python programming because PyTorch usually requires classes to work. So here we create a class custom image dataset. It inherits the dataset properties. And as we said, in the init function, we have the path to the annotations file, the path to the images, and any transformations you want to perform. And when we first instantiated it, it will go read those and load them up for you. The second one that you need to define is the len, which returns the number of examples in your data sets. In this case, we just return the length of the labels, which is the same number as the example we have. And then lastly, you need the getItem function. That what that does is it loads and returns a sample from data set when you specify it by a given index. So in the getItem here, we have the index as an input, and we get the path to that image. We read that image, we get the label, and if we have any transformations defined, we apply them, and otherwise we'll return the image on the label. Second thing we need to do is define the data loader module, which is, this takes a data set and abstracts all the behind the scenes functions you need to do and basically creates the mini patches for you, shuffles it, and it's ready to load to your network. By default, this is this runs on a CPU and there's no way to transfer that into a GPU. That's something we need to do later, just something to have in mind. And also by design is multiprocessing, so it should take advantage of all the cores on your CPU, so it should still be fast. Here we create two data loader objects, the training set and test set. We define a batch size of 64, and we also, every time we run it, we shuffle this around. As a first step, let's try the simplest form of a neural network, which is a feed-forward neural network. It's a fully connected feed-forward neural network, and in this time we can have two hidden layers, each with 512 units, and it all comes from the torch.nn method. Again, you need to be a bit comfortable with object-oriented programming here. When you define the neural network, it has to be in a class, and you need to inherit the nn.module properties. In the init function, what we do is we define all our layers. And first, it's always a good idea to have that super function, which allows us to access methods and properties of a parent class. So in this case, the nn module. Because we're dealing with images and it's a square tensor of 28 by 28, we need to flatten it. So we make it convert it to a vector, and we can do that using the flatten layer. And then we define a sequence of fully connected layers based on the size of the input we have, which is in this case, the first layer is when you flatten the image, you create a vector of length 28 by 28. Out features is the number of hidden layers we have. As we said, we're going to use 512. We're going to use a ReLU activation function. Then another linear hidden layer, 512 hidden layers. And then in our last layer, which is the output, we're going to have as an input 512 and output 10 layers, which is the number of classes we have. In this case, we're not going to use a softmax activation function. So basically, we're returning a vector of logits. We're going to need to use the argmax function later to decide on which class is the most probable based on our neural network. Next, we define the forward method, which basically defines how data flows through our neural network. In this case, our input is X. X goes through the flatten layer that we define above. Then we create the logics by passing it through this linear ReLU stack that we created, which is a sequence of five layers. And we return the logics, which is the output of our model. Let's run this. Next, we need to create an instance of the model. And if we print it, it will return an overview of our architecture. We have 28 by 28 is 784 input units, 512 in the two hidden layers, and then 10 output features. By default, we will have bias enabled. Again, it depends on the architecture. If you don't want it, you can manually turn it off. So we defined our neural network, and now before we start training it, we need to define a few hyperparameters. And what does anybody know what hyperparameters are? Hands? So hyperparameters are a set of parameters that you can adjust, and you can control the optimization process and can impact the performance and convergence rate of the model. Some examples that we regularly use in neural networks is the number of epochs. So how many times we iterate over our training set, the batch size, and how big, how many examples we feed into the neural network each time. And that also dictates on how many times the backpropagation method is gonna be applied. The learning rate, which is how much to update the model's parameters at each batch or epoch. And this is something that you need to be a bit worried before you start training it. There's always trade-offs in these kind of things. I mean, you can have infinite epochs, but then you're running the danger of overfitting. You can have very small or very large batch sizes, but then you can have very long training time, so impact the performance of your model. The learning rate can be too low, so your model might be too slow to learn, or too high that it doesn't learn. So you always need to find a balance between all those two. There's a few different starting values that we can use, but be wary about that. Another very important thing is the loss function that we choose. And again, that always depends on the type of neural network you're training. If you're doing a regression model, then root mean square error might be good. If you're doing classification error, root mean square error is useless. So in this case, we're going to use the cross entropy loss function, which is a common metric just to measure the performance of classification models. This normalizes the logits and computes the prediction error based on ground truth. We also have the optimizer, which basically dictates how this process adjusts the model parameters. And in this case, we want to use stochastic gradient descent. Another popular one is Adam, and there's a few different variations of it, like AdamX or Adam Delta. You can have a look at all the different optimization methods that are available in PyTorch in this link. So when we initialize the optimizer, we need to register the model parameters in there, so it knows how to optimize it. Basically, we define the learning rate. Usually something like 1 × 10⁻³ is a good starting point. We initialize with batches of 64. We're going to train for 5 epochs, and loss function, as we said, is cross entropy loss. And we pass all this into the optimizer, which in this case is a stochastic gradient descent. And finally, before we start training, we also need to define the training loop and the test loop, which is basically a function that will perform the forward and backward propagation steps and call the optimizers to adjust the parameters of the model. In the training loop, we need to give the data loader object as an input, the model, the loss function, the optimizer, and lastly, the device. First, we need to get the size of the mini batches. Let's have another one here. We have 60,000 examples in our training set. We get these, but then if we call the actual length of data loader, that's 60,000 divided by 64, which is the batch size, so it's 938. So we loop through each batch in the data loader object. Later, when you're going to use GPU, we need to move each batch to the GPU. This is important because, as we said, data loader by default runs on the CPU. We're going to use our model to basically, this does the forward propagation. We're going to pass the the mini batch through the model to get the prediction and calculate the loss based on that prediction and the ground truth. And then we're going to perform the backpropagation procedure, which also updates the parameters. We call the zero grad method, do the backward propagation, and then optimize for this step. And this is just something to keep an eye on how things are going. In the test loop, we do something similar. We just don't run the backpropagation procedure because we just want to see how a model performs in the test set, and we don't want to update the parameters there. We calculate the size, the number of batches, and then we define the test loss and how many correct answers did it get. We initialize them equal to 0. It's important to run it with torch no grad, so it freezes the weights and it doesn't update them because we don't want to, because we're just testing and we're not optimizing. And then again, we loop through the batches in the data loader, in this case, the test data loader. If we're using CUDA, we send everything to the GPU, calculate the prediction, update the loss, and then see how many we got correct and how many we got wrong. In the next step, we're just gonna see how this runs. So we're gonna run for 5 epochs. We have the time command on top, so we know how we time it. For people that are running on Google Cloud, that's gonna be a bit slower for you. Already have epoch number 5. So yeah, on CPU that took 26 seconds. And we got a final accuracy of 48%. Jeez, bad. Anybody know why this is bad? Excuse me? Well, we're using a feed-forward neural network to guess images, and it's generally not a good idea. We didn't optimize it. We ran it for just 5 epochs. There's a lot of reasons for that. Next, we're gonna try and run it on GPU. So again, we define the neural network again, create a new instance, and this time we send it to the CUDA device. We need to define another optimizer because optimizer we had before got the parameters from the model that we run on the CPU, and basically run it again. So that took 24.7 seconds, and on the CPU took 26 seconds. That's not much faster. Can anybody guess why? Yes? Sorry, I didn't hear you.
So at the moment, the overheads are more and we are using less number of epochs. That's right. Perhaps when we use more number of epochs, we'll see better performance on GPU.
Yes, and there's some other things as well. So when you're running these kind of methods, there's all sorts of overheads. Each time you're reading the data and you're loading into the memory. So in this case, because our model is simple, the actual computation of the parameters and the backpropagation takes much less time than all the input-output that you're performing. So training time is not dictated by the actual performance of the CPU or GPU, is dictated of how fast your method can read the data and load them. But again, we got 54.7%, which is again not great. So as Mihalis and Konstantinos talked a lot about before about convolutional neural networks, we're gonna try and implement one here, which usually outperform PyTorch neural networks for image classification problems by far. So before we start, first, what is a convolution? It's just a mathematical operation that is operated to extract features from an image, and it's defined by image kernel or a small matrix. In this case, what we're trying to learn is the weights of this kernel, so our model is able to detect the proper features for a classification problem. When you're doing convolutional neural networks, though, because of this kernel, there's always dimensionality reduction in your data. So there's a few ways that you can avoid that. One of them is padding. In this case, we have a 3x3 matrix and a 2x2 kernel. And in order to not shrink our initial matrix to 2x2, we add a padding of zeros around it. And this is called padding equals 1. You can add, depending on the size of your kernel, you can add more. Or if you don't mind losing dimensionality, again, you can add nothing. And sometimes when you're trying to learn some more higher level features, you might want to use stride. Stride means how many steps does your kernel does when you scan through your matrix. So with a stride equals to 1, it will go in steps of 1. Stride equals 2, it will do in steps of 2, and so on. Again, it depends on what you want to detect in your image, or if it's another task. Having a high stride can make your network much faster, but can also lose accuracy. So again, it's always a trade-off. And in order to calculate the layers, when you're doing convolutional networks with padding and strides, you can use this formula. Basically, if you have an n by n matrix as an input with an f times f matrix with stride equals s and padding equals p, you can use this formula to calculate the layer sizes. It's important to keep track of that because, as you see, when you try and write the code, you have to be consistent with that. A few other layers we use in this kind of networks are pooling layers, which we intentionally progressively use them to progressively reduce the spatial size of the presentation, and then can massively reduce the number of parameters of your neural network. So it's gonna be much faster and less complex. Again, use this sparingly because it's not always necessary, and sometimes you might over reduce your complexity and lose performance. There's two very popular pooling layers. One is max pooling. So you have like a 2x2 kernel, you get the maximum value of that, and this is your output. And if you have an average pooling, then you get the average of those 4 values. There's also a patch normalization layer, which is a method to make training your network more stable and efficient. And what that does is basically takes all the weights and biases from a layer and recenters them and rescales them so they're a bit consistent. That has been proved to make your networks more stable and efficient, and it's a good idea to use it. And lastly, we have dropout. And this is a method that between layers that you can use. So in dropout, you define a probability, let's say 20%. And with each pass, you randomly disable 20% of the weights in that layer. This is in each pass, this random deactivation of layers changes. So sometimes you deactivate a set of one set of them and then another set, and this way you can regularize your neural network and then you can prevent overfitting. But be careful, don't use batch normalization and dropout together because it can lead to unexpected results. So we're gonna define a very simple convolutional neural network. We're gonna have two convolutional layers to start with, both with a kernel size of 3 times 3. The first one, we're gonna add padding equals 1 and stride equals 1. We're gonna have a batch normalization layer in there, a relu activation function, and a max pooling layer in the end. In the second one, we're gonna remove the padding, so we reduce the dimensionality of the layer, so we make it a bit faster. This is then passed into a fully connected layer, so we're gonna learn a representation of our features in latent space in the first one, in the first two convolutional neural networks, and then we're gonna pass it into a fully connected layer, so we can have a classification. In the fully connected layer, the first one is going to have 600 units. We're going to add a dropout of 25%, then down to 120 units. And then finally, our 10 unit, which represent our 10 classes, is going to be the output. And we can see that. So again, we define a class, we call it confnet. We inherit from the nn.module class. The first layer of convolutions, we're gonna have it in a sequential manner, starting with the convolution layer. Because it's a grayscale image, we only have one input channel. If you have an RGB, then this would be 3. We're gonna go from 1 channel down to up to 32 channels as an output. The kernel size is defined as 3 and padding equals to 1. Then batch normalization takes the number of channels, which is 32, relu, and max pool layer. I think you can have a look on this on your own. Let me know if you have any questions. And then again, in the forward method, we pass through all the layers until we reach our output. Yes? Yes. So that means we have a 6x6 tensor with a depth of 64 channels. So we go from 1 channel to 32 channels here. When we apply kernel size equals 3 and padding equals 1, we can go up to our formula here. So we have 28 plus 2 times the padding is 30. We have 3 by 3, 27 plus 128 over stride, which is 28. So you get the point. But then the max pooling shrinks down to 14, and then that further shrinks it to 12. Again, we have another max pooling divided by 2, so we got to go down to 6. In the latest versions of PyTorch, they introduced some new features called lazy layers. So you don't need to do that, it figures it out on its own. So instead of having conv2D here, you have lazy conv2D, and it's supposed to figure it out on its own. I don't know, I never got it to work properly, so your mileage may vary. It's supposed to be better now, but I haven't used it in the past year, so I don't know. So let's run this. And again, we create a new instance of the convolution neural network. By default, this is instantiated on a CPU, and we haven't moved it to the GPU yet. Start with a linear of 1 to the times 10 to the minus 3, 5 epochs, basically more or less the same procedure as before. But now we see it takes much longer. Can anybody have a guess why it takes much longer? Yes? Can you press the button on your microphone? It takes longer compared to the no, why it takes longer compared to the one we ran before, to the feed forward one.
We have network parameter, so long
Exactly. So with the feed forward, I think we had about 20,000 trainable parameters. Now we have, I think 1.7 million, if I remember correctly. So orders of magnitude more parameters to train, and orders of magnitude more operations to work through. So we're at 1 minute, 15 seconds, and it's still going on mine. I think it takes about 6 or 7 minutes on people that's running on Google Colab. So if you have any questions, now is a good time to. Yes? We just drop out the, no, we drop one layer, one channel. It's just to keep the dimensions constant, so we don't need to do something more. It was just a way to make it a bit simpler to work through. This is by no means the best solution to this problem. It's just one we can run in 5 minutes when we can talk about it. So for me, it took 2 minutes and 5 seconds. Is Google Colab done, or is it still going? How long did it take on Google Colab? Okay, so. And again, now let's start on the GPU. We send it to CUDA. I think it takes about 45 to 50 seconds on mine. So does anybody have any guesses? Why is it faster on GPU? No. So a CPU basically is made so it can do anything. You usually have 8, 6, 10 cores that are very large, and they're multi-purpose, so they can do anything. In GPUs, we have thousands of small dedicated units that can do very quick matrix operations. So what PyTorch does is basically massively parallelizes all the operations to run on very simplistic cores on GPU, but that are very good in doing matrix manipulations. And in this case, it's usually matrix multiplications. So if you're as we've seen, if your network is small, then you're not gonna see much difference going from a CPU to GPU. But if you're starting to get to a larger network, in this case, just a simple one with 2 convolutional layers, fairly small, got us from 2 minutes and 5 seconds on a CPU down to 28 seconds on GPU. So imagine if you have thousands of blocks of convolutions and attention layers in there and a few billion examples to train on, that can scale very fast at very large scales. Models like the ones that were presented this morning, like large language models, took hundreds of thousands of GPU hours to train, costing hundreds of thousands of dollars to train, up to millions. And basically, this is not possible to do on a CPU. That kind of scale, it's, even if you use all the CPUs of the world, it might still not be possible. So that was more or less what I had to show. I have a few exercises below if you want to try them out on your own and ask me if you have any questions, or if you have any questions that you want to discuss, I'm happy to hear you. Yes. Yes. I mean, we can have a look here. It's still multiprocessing it still does multiprocessing on the CPU. So yeah, you can see it's not utilizing 100%, but it's, yeah, they have 16 threads, it maxes out 8 of them. But again, it's 8 threads against 3,000 CUDA cores, I think the 36 I have on my laptop has. And that's a laptop GPU. Just imagine a full scale AI dedicated processing unit. Any other questions? Yes. Yeah. Yes, that's the convention of PyTorch. That's how you do. In the latest one, you have the option to also compile it, so you make it a bit faster, but you always need like an init function that you define the layers, and a forward function that you define how the data flows through the layers. Basically, the point of the session I was trying to do today is not to teach you how to do neural networks in PyTorch, is give you an overview of how PyTorch works, and you have a reference of if you want to do something quick, you cannot pin this and either copy these functions and modify them, or go to the links that I have in there. So you can have like a quick reference. I mean, it's not possible to teach that in an hour. So shall we go on to the exercises? So initially you had a batch size of 64. If we run it, I think it took about 25 seconds. Any guesses on what happens if we increase that to both training time and the accuracy in 5 epochs? You want to try it and let me know? So we got 83.5% and 26.2 seconds. If we do, let's say, 256. So training time was decreased to 20.9 seconds, but also accuracy was decreased to 75.9% from 85. Any guesses why? Yep. Exactly. So as we said before, the backpropagation, we update the parameters each time we do the backpropagation step. If you have this time 4 times higher batch size, it means we're doing 4 times less backpropagation steps. But on the other hand, it's also about 20% faster. So what I'm trying to say is batch size is just another hyperparameter that you need to optimize based on what you have in hand. There's data that the network is very large, so just in order to fit the parameters in the GPU memory, you can only process one example at a time. In this case, we might be able to process all of them at the same time. So if we try, say, 10,000, yeah, we can still fit them in the GPU memory, but we're gonna see that accuracy sucks at 5 epochs because we only did what 30 backpropagation steps. So when you updated the parameters 30 times, which is not enough to get good results. Also, number of epochs is another hyperparameter you need to think about. If you have a high batch size, your neural network is faster, but you also need more epochs to reach the same accuracy. Also, yeah. Yes. They're shuffled. You can define that so they don't. In this case, we define so it is. So if you go on to the second exercise, yeah, play around a bit with the learning rate of the model. How do you think this will affect training? Just a guess before you run it. Let's do something very small, like 1 to the times 10 to the minus 9. Accuracy 9.5% and 26 seconds. Why do you think it scored so low there? It's basically a random classifier because you have 10% to get one and correct at random. Any ideas why it didn't learn anything? We reduced the learning rate from 1 to the times 10 to the minus 3 to 10 to the minus 9. So 1,000,000 times smaller. To 10 to the minus 3 to 10 to the minus 9. So it's yeah, exactly. What we're doing in gradient design is basically using the gradient of the error to go through, to travel to an optimal position when you minimize the error of your neural network. If that learning rate is too small, then those steps are too small. It's going to take forever to reach there. On the other hand, if you have something large, so let's say 100 here, doesn't learn anything because it reached some random peak. So it's exactly 10%. So it's exactly random classifier this time. Usually a good starting point for a learning rate is something around the 10 to the minus 3, 10 to the minus 4. We usually start from there and work our way through higher or lower numbers depending on how the model looks. Yes, so there's other techniques that you can use. There's adaptive learning rate. So you start with, let's say, something like this, 10 to the minus 3. And as training progresses, you slowly decrease that. So as you approach local or global minimum in the error space, then you start to decrease your learning rate. So you stay there, so you don't jump somewhere else that it's not optimal for your network. Yeah, thank you, Andrea. And on the third one, try to add another convolution layer to the neural network and run it again on your own. I would say do one after layer 2 to add a third layer that takes 64 channels as an input and outputs 128 channels. And basically follow the architecture of the second layer, add a max pooling layer and a kernel with a kernel size of 2 and stride 2, and also a batch normalization and railroad activation function. So I think this is that convolution layer I was talking about. Any idea what else we need to change after we add this? And exactly. Do you know how they change this? So you go from a 6 times 6 here, you add a kernel size of 3 without any padding. So you lose basically you lose 2. So you go down to 4 by 4. And then you also have a max pooling with kernel size equal to. So what do we put here? So number of channels, as we said, is 128. Exactly. And we also need to put that into a forward one. So I think that should be fine. Yep. So we have about 10 minutes left. Anybody want to ask something? Any questions about what we talked about? PyTorch in general, neural networks in general? Yep. There? So in which one? the feed forward. Here. So as we said, in a feed forward, fully connected feed forward neural network. Come on. Your input is a vector, so it's a one dimensional array of values. But we have images, which is a square matrix of values, in this scale, grayscale. So because it's grayscale, when you have a 28 by 28 matrix with values from 0 to I think is 256 bit. So in order to go from that square matrix and be able to fit it into a feed forward neural network, we need to flatten it. So we go from, and because it's 28 pixels by times 28 pixels, when you flatten it, the total number of pixels in that square is 786, 28 times 28. So you basically take you take the first row, the second row, put it next to the first one, the third one, and put it onto, basically you do that until you end up with a one-dimensional vector. And in, where is it? So this is what basically happens here. You reshape that square matrix into a flat one. So you go from 28 times 28 matrix to a 786 times 1 vector. Is that okay? Which one? This one. Sorry, and what was your question again? Annie? Was that, you want to ask something about this? The number of the matrix, it figures out on its own. So you go from a 28 by 28, channel size equals 3 and padding equals 1. So you maintain your I think it decreases a bit. Then when you do the max pooling layer, you have a kernel size equals 2 and stride equals 2. So you have that. So you go from a 28 by 28 to 14 times 14. Is that correct? Yeah. And then you have another kernel size equals 3 in your second layer. So 14 minus 311. 12, sorry. Yeah. So 14 minus 311 plus 1, 12. And then you have a max pooling layer of 2 with stride 2, and that basically helps it. Look into how also the pooling layers affect the sizes of the matrices. It's in this link that I have here. Yeah.
Question from someone online. It's Andreas Hachipkiris, and he asks, can you if you had no memory or time limitations, would it be better to apply gradient descent on the whole data set, or do STG on only one data sample at a time?
If your memory can fit the whole thing and you can run and have infinite time, then both will work. if you use the whole data, in this case, we might be able to use it because the data set is small and the number of parameters is small, so you might be able to fit it all in memory. And doing gradient descent, basically do one pass over the whole data set each time. Or do it one by one, it's gonna take time and iterating. But probably I would do the full batch if I could, but I'm guessing the results will not differ that much if we had infinite time. Yes, it's always an interplay between all of the hyperparameters. When you increase one, then it affects either another one or a set of other ones. So you need to be a bit careful on how you configure all of them. And most of the times it's not possible to just try everything and see how it affects, because in this case it takes a minute to train the model. Other times it takes weeks. So you need to be a bit smart on how to choose these things. Or start on a very small subset of your data, try a few things, and then do training on your whole set. Yes. Yeah.
Why didn't like say, I guess there was enough time to develop a more sophisticated
There's plenty of optimization methods. There's Adam is another one very popular.
Sorry?
There's a lot of optimization methods available now. There's Adam is another one very popular, and most of the times it outperforms gradient descent. It's just I chose gradient descent in this time so I could tie it on why we need the gradients as well.
Yeah, okay.
There's no specific need to use gradient descent. Yeah, it's just one of the methods that I use today. This, as I said, this is by no means the best approach to this problem. It's just something that worked in an hour, so we can talk about it. There's also a lot of already made pre-trained architectures, including PyTorch, like ResNet, which is residual blocks of convolution layers. And you can take that, you can download the network and its weights, and you can either add a couple of layers at the end or fine tune it a bit to match your needs. So you save a lot of time, and you basically download something that you already know it works on this kind of tasks. But of course, that's a much larger model, and I wouldn't be able to train it on my laptop in 5 minutes. And basically, it's easier to write the code for that because you don't need to write the layers, they're already made.
Okay, thank you.
Anybody else? Yes? Yeah. Can you talk into the mic so the people online can hear you as well?
Can you hear me?
Yeah, thank you.
Perfect. So for the hyperparameter tuning,
Yeah.
For example, in machine learning, we use like cross-validation, right? You split the data, the training, blah,
Yeah.
blah, and you evaluate on the external set. So in this case, you would select from what you have presented so far, my understanding is that you would select the hyperparameter based on the outer set's performance.
Oh, you can follow the same principles as machine learning here. It's just we didn't have time to cover everything. I mean, if you have enough time and enough data to do cross-validation, it's always a good idea to do it. It's not because this is a neural network we omit doing conventional machine learning methodologies.
My question is more like, what's your recommendation? Basically?
Excuse me?
What is your recommendation on to optimize the hyperparameters?
if you can run, if your model is small enough so you can run a few iterations to get a good idea of where roughly your ideal set would be, do that, and do that on a reduced training set, and then do a few more iterations on your full training set with a range close to your chosen hyperparameters, and then you basically choose the best one from there. If it's not possible to do that, there's a few papers that the people discuss on how to choose hyperparameters beforehand, but that's completely out of the scope of these talks. So I would suggest go over there. There's a lot of talk about that because, as we said, with large language models, it's not possible to train like 50 of them and choose the best one. You choose the hyperparameters, train it, and that's it, because it already costs you like $1 million. So there's a few ways that you can make an educated guess on where your hyperparameters lie. There's always a few good starting points as well. Like we said, learning point -10 to the -3 is usually somewhere around there. Usually, it's not always. Depending on your problem, choose the correct optimizer, choose the correct loss function. Take a few steps to limit overfitting, like dropout and maybe in batch normalization, something like that in your network. And if you let it run for a few more epochs than necessary, it's not a huge problem usually. Anybody else? We have 1 minute left to one. I don't know if we.
Thank you, Bandeli.
Thank you very much.
Thank you everyone for your questions. We now have a half-hour break, okay? We have a seminar in, in half hour. So please go outside, have lunch. People online, the seminar is at the same link, so it's the same Zoom session. So see you in 25 minutes. Please be back. Thank you.